Okay, g'day all and welcome to another video. So today I want to talk more about the AES algorithm and start filling out some of the functions that we were talking about last time. So there's 4 steps in the rounds of AES and today we'll talk about 3 of them. SubBytes, ShiftRows and AddRoundKey. And we'll leave MixColumns for a different video because it's a little bit fiddly. Alright, so just an overview of what we're doing here today. I've highlighted the rounds that we're tackling today in blue. Yeah, so we're approaching halfway, I think. Yeah, after today we'll probably be about halfway through the algorithm of encrypting with AES. Key expansion and MixColumns are the other 2, but they're pretty fiddly, so yeah, we'll leave those for different videos. Alright, before we get started, I just want to fill in some of the parameter passing that we're going to need in our code. So if we come over here to our code, the first thing I want to do is this initial round function just here. This is actually just AddRoundKey. Yeah, so in our encrypt function, we just want to change that for AddRoundKey. Yeah, it's the same thing. The whitening step is the AddRoundKey function. What else have we got? Well, the SubBytes step takes the state as a parameter. ShiftRows takes a state. MixColumns takes a state as well, but we'll fix that up next time. AddRoundKey takes 2 parameters, the state and a round key. Today we haven't got round keys, we've actually just got a key because we haven't done this key expansion step just here, but eventually we'll have different keys for each round. Anyway, let's just keep filling out these parameters. So the AES encrypt function itself takes a message and it also takes a key. So we'll just say key like that. It's common to copy the message to a separate array called the state and work on the state, but you could encrypt in place in the message if you wanted. Yeah, but we'll just encrypt in blocks. This is a block cipher, so we'll just encrypt in blocks and we'll copy these first 16 bytes to our state just here. Just like that. Okay, so we'll pass the state and the key to our AddRoundKey function. And like I said, this is actually going to be different keys for each of these AddRoundKey calls, but for now we'll just use a single key. The SubBytes function takes the state as a parameter, ShiftRows takes the state, and AddRoundKey takes the state and the key. Or the round key it will eventually be. SubBytes takes the state, that takes the state, and this takes the state and the key. Okay, so that's just about all of the parameter passing except for MixColumns and key expansion, which we'll work on next time. Another few changes I might make. I might change our message to unsigned characters instead of characters. It doesn't make a big difference, but yeah, I've just used unsigned chars up there, so we might as well use unsigned char down here. Message and key. Okay, I think that's about all we wanted to do for our parameter passing. So now we're passing our state around in our functions. We've got to figure out what the functions actually do. So here's the first one, SubBytes. What does the SubBytes step do? Well, all we do is we look up a substitution for each byte in our state in this Rindale S box. So the S box is just a grid of 256 byte substitutions written out in 16 rows by 16 columns. So Wikipedia has the S box available for us. So if we just jump over to Wikipedia, you can just Google S box. I mean, this thing's available freely online. If you scroll down a little bit, you'll come to this table. This is the S box written out nicely if you happen to be doing AES by hand. Not that you ever would. But all we're doing is for each byte in the state, say one of our bytes is 4D in hexadecimal, so it has the value 4D. All you would do is you would come down here to the 40 row, or the 40 row, and you would go across to D, and you would see that 4D is to be replaced by E3. Yeah, so this is the S box just here. This is the S box itself. Just a bunch of replacements for your bytes. If your byte happened to be C3, then you would come down here to the C row, and you would go to the 3 column, and you would see that the byte C3 in the state is to be replaced by the value to E in hexadecimal. Good stuff, but if you scroll down a little bit further, you see something even cooler, and that's that the Wikipedia page actually has the S box as an unsigned character array, which is perfect for us because we can just look up this as a 1D array and make all of our replacements really, really simply. Alright, so you don't want to type this out, you just want to copy it from Wikipedia or some other source. Just copy the S box and paste it into your code, just like that. And down here in the SubBytes step, let's fill out the body. Okay, so for int I equals 0, while I is less than 16, I plus plus. So for every byte in the state, what we want to do is replace it with the S box value. I might just call this S box instead of just S because it's a little less cryptic. Yeah, simple as that. So each value, each byte in the state becomes whatever the index of that byte is in the S box. Alright, so moving along, that is the SubBytes step. Alright, so before we go any further, I want to mention that it's common to write out the state and the round key, though mostly the state for what we're doing here today. It's common to write out the state as a 4x4 grid. So if our message was what is a Creel, with the W being byte number 0 of our message, and the question mark being byte number 15 of our message, you would write it down like this. So you write the what, the first 4 characters in the first column, then you fill out the second column, then the third column, then the fourth. Good stuff. It's just better to imagine that's the way your state is laid out, because when we come to ShiftRows, it's really, really helpful. So in ShiftRows, what we do is we take that state as imagined as a grid, and we shift the first row by 0 to the left, or we don't shift it at all, in other words. The second row we shift to the left 1 byte, the third row we shift to the left 2 bytes, and the final row we shift to the left 3 bytes. And as bytes are shifted out on the left, they actually reappear on the right. So this operation is sometimes called rotation. Yeah, rotation. Let's have a bit of a demo. So here I've written out the state as indices. So this is byte number 0 just here, byte number 1, 2, 3. Yeah, but these will be letters of your message, really. Letters of your state. If I just copy this and paste it over here, we can have a look at exactly what's going to happen to this state once we perform ShiftRows. So the first row doesn't get shifted at all. The second row gets shifted 1 byte to the left, just like that. But as bytes are shifted out on the left-hand side, they actually reappear on the right-hand side. Yeah, just like that. So that'll be the second row of our state after ShiftRows. The third row gets shifted 2 bytes to the left. Something's happened. Okay, that's 1 byte and 2 bytes. But just as before, as bytes are shifted out on the left, they pop back around and reappear on the right. And the final row gets shifted 3 bytes to the left. So that's 1, that's 2, and that's 3. And once again, the bytes reappear on the right-hand side as they're shifted out on the left. Okay, so that's what the ShiftRows operation does when you imagine your state as written out as a grid. So you can see that it's really, really handy because now all we've got to do to code the function is just look at what these bytes correspond to in the input and output. Let's have a bit of a look how that works. We'll come down here to ShiftRows, and I might make a unsigned char, array called temp. I'll make it 16, and we'll perform the actual shifting in this TMP variable here, this temporary array, and then we'll copy it over to state. Alright, but what are we going to do? Well, byte number 0 of the state remains as byte number 0 in the output. So we can say TMP 0 equals state 0. Byte number 1 of the state becomes byte number 5 of the output after ShiftRows. So we want TMP 1 equals state 5. Byte number 2 of the state becomes 10. And byte number 3 of the state becomes 15. You see, so we're just looking at what the corresponding values are after the shift. It's pretty simple, actually. 2 becomes state 10, and 3 becomes state 15. You could do this with a for loop as well. You know, you could do this all with a loop, but it would be confusing and probably slower. So I think this is a better way to do it. Just write it as an unrolled loop. All right, I'm just going to do a bit of copying and pasting here so we can speed things up. This is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, so we've done the first column. The second column, 4, 5, 6, and 7. 4, 5, 6, and 7, that's the second column. That becomes 4, 9, 14, and 3 after the shift. So 4, 9, 14, and 3. Okay, moving along to the third column, that becomes 8, 13, 2, and 7. 8, 13, 2, and 7. And the final column, the 12, 13, 14, and 15 indices of our state are shifted after shift rows to 12, 1, 6, and 11. So let's just write that in, 12, 1, 6, and 11. Alrighty, so once we've done our shifting in TMP, we want to copy that over to state. So for int I equals that to 16, I plus plus, and state I equals TMP I. And that, my friends, is the shift rows function. Good stuff. So you see, it's really easy to imagine shift rows when you can kind of envisage the state written out in a 4x4 grid. All right, so moving on to the final function. So this AddRoundKey step is actually super simple, as we'll see in a moment, but I'm going to confuse things a little bit because I'm going to take the opportunity to introduce Galois fields. I don't know if this is the best time to do this, but the MixColumns step that we'll look at later is already confusing enough. So, you know, I'd like to get Galois fields introduction over and done with before we get to that to hopefully save some time. All right, so let's have a look at Gimpy Gimp and explain what on earth a Galois field is. Finite fields, they're sometimes called. Galois was a French mathematician back in like the 1800s, I think. Anyway, he did some interesting work, so let's have a bit of a look at what he reckoned. If we've got a number, say 5, 7, 3, and we want to imagine this as a finite field or a Galois field, what we say is that this 3 just here means 3 by x to the 0. And this 7 just here means 7 by x to the 1. And this 5 just here we say means 5 by x squared. We don't usually use base 10 like we're using here. Like 573 is, you know, in decimal it's 573. But usually we actually use prime bases and powers of primes. But we'll look at that in just a second. Okay, so as a Galois field, this is just written out as a polynomial, something like this. So 573 means 5 by x squared plus 7 by x to the 1 plus 3 by x to the 0. So you'll see that it's basically the same as normal decimal, except that the x just here in decimal has a set value. It's 10. Yeah, this 5 just here literally means 5 by 10 squared. Okay, so if you want to add polynomials together, say we've got a plus just here, and we've got a 6, and maybe we've got another 7 and a 2, something like that. If these were two polynomials, well, 3 by x to the 0 plus 2 by x to the 0 gives you 5 by x to the 0. 7 by x to the 1, I'll just write x to the 1 down here, and x to the 1, and x squared, and x squared. 7 by x to the 1 plus 7 by x to the power of 1 gives you 14x to the power of 1. But using Galois fields, what we actually do is only take the remainder after division by some base. So our base in this instance is 10. What we would do is scrap the 1 just here and just use the 4 as our answer. Yeah, so what we're really doing here is called addition modulo some number. And the number in this case is 10, our base. I want to mention again that you would never usually use 10 for Galois fields because 10 is a composite number. Usually you use prime numbers and powers of primes. Yeah, but for now, just as an explanation as to how to add these fields together, we'll use 10. All right, but 5 by x squared plus 6 by x squared would normally give you 11 by x squared. But using modulo arithmetic, we scrap the carry and we just end up with 1 by x squared. Yeah, it's as easy as that, really. So all we're doing is scrapping the carry. So if we had something like 9, 4, 3, 2 plus 8, 6, 1, 5, for example, if you want to add those together using these Galois field ideas, all we do is add normally, except we don't carry. So we'd have 7, 3 plus 1 gives you 4, 4 plus 6 gives you 10, but we're scrapping the carry, so we don't do that. We just write the 0 in the answer. And 9 and 8 gives you 17, so we scrap the carry and just write the 7. It's as easy as that, really. So if we move over to binary Galois fields instead of this decimal one, our state will have a bunch of bytes, 16 bytes. If we write one of those bytes out, it might be something like 1, 0, 1, 1, 0, 1, 0, 1. All right, so say that's a byte in our state. That's our state right there. A byte written out in binary, so there's 8 bits in a byte. This 1 just here means 1 by x to the 0. This 0 just here means 0 by x to the 1. It's a Galois field. You see, it's one of these polynomials. X squared, this means 0 by x to the 3. This one means 0 by x to the 4. This is 1 by x to the 5, 0 by x to the 6, and 1 by x to the 7. So that's what the state's byte would mean if we write it out in this rather cumbersome fashion as a polynomial. All right, and we're also going to have a corresponding byte in our key. So say our key has something like 1, 0, 0, 1, 1, 0, 1, 1. That might be a byte in our key. And what we hope to eventually do is add these together. So once again, this means 1 by x to the 0, 1 by x to the 1, etc., 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 all the way over here, and this one means 1 by x to the 7. Okay, so we're going to add these two together using them, using the modulo arithmetic, just as we did in base 10, only now we're in binary. Now we're in binary. Okay, so in binary, what we end up doing is, if we have two inputs, A and B, and an output, learn how to spell. What's that? A W with an O on it. 0 plus 0 in binary is 0. 0 plus 1 in binary is 1. 1 plus 0 in binary is 1. And 1 plus 1 in binary is 2. But because we're doing modulo arithmetic here and our base is 2, we scrap the carry. And we only take this final digit. So what we end out with is, well, what's called a truth table, really. 0 and 0 gives us 0, 0 and 1 gives us 1, 1 and 0 gives us 1, and 1 and 1 gives us 0. So we can go through and fill that out. So 1 plus 1 gives us 2, but we scrap the carry and just write the 0. 0 plus 1 gives us a 1. 1 plus 0 gives us a 1. 0 plus 1 gives us a 1. 1 plus 1 gives us 2, but we don't write the carry. 1 and 0 gives us 1, 0 and 0 gives us 0, and 1 and 1 gives us 2, but we don't write the carry. Okay, so that was a little introduction there to Galois fields and imagining our state and our key as polynomials. And also a little introduction as to how to perform arithmetic on mod 2. Yeah, so this will become really important later on when we do another operation which is possible on Galois fields, and that's multiplication. Yeah, so you can actually do multiplication, subtraction, division, and addition to Galois fields, but today we're just looking at addition. All right, but what's quite nice about this particular output just here, and what you might have noticed if you've spent any time programming computers at all, is that this happens to match the truth table for a very, very useful operation, the one and only XOR, people. All right. XOR is what we're doing. Yeah, so the addition of two Galois fields, mod 2, is exactly the same as XOR. Good stuff. Long story short, that was more like short story long. Let's come over here to AddRoundKey and code that up. All we've got to do is XOR. For int I equals 0 while I is less than 16, I plus plus, state I XOR equals round key I. And it's as easy as that, but hopefully now that we've introduced this idea of looking at our values as polynomials, hopefully mixed columns becomes easy to explain next time. Yeah, binary addition, mod 2 is just XOR. Galois fields are cool. Anyway, that's about all that I wanted to say. So if you like what I'm doing here and you want to support these videos, head over to Patreon. This particular video today has been really difficult to record, and if you like what I'm trying to do, head over to Patreon and become a supporter. The other thing I want to mention is I've got a Facebook where I occasionally upload information on upcoming videos and also some of the projects I'm working on. So I started working a little while ago on a chess front end for UCI engines. Hopefully it's going to have some AI, and hopefully it'll be able to describe with prose lots of things about your chess position and improve your game. I haven't decided where to upload it yet, so if you've got any good ideas about where I could upload my chess program so that playtesters can test it, just leave a message in the comments. Anyway, links in the video descriptions, and I want you all to have a really good day. Thanks for watching. See ya.